In section 11.2 we look at coordinates in space. We're looking at 3 dimensions here, and so first we need to be able to kind of visualize what we're actually talking about. We live in a 3-dimensional world, and so we get that, but we don't. In math we so often focus on just 2-dimensional things, xy plane, etc. Now we're going to look at the x, y, and z coordinate axes. In order to do this, you can notice that in this case we have an x-axis coming out this way, a y-axis going this way. So it's a little different than what you're thinking. So we kind of rotate things, and then we put the z-axis goes vertically. If you want to think about it, you could point your finger and your first 2 fingers out as an x and y-axis, and your thumb becomes the z-axis going straight up. If you want to give that a try. Anyway, we have coordinate planes here. The xy plane is the flat plane, if you would, here. It's right here that passes through the x and the y axis. The xz plane would be this one right here, which you can kind of see. And finally, the yz plane is the one that goes through the y-axis, and it's harder for me to get this one right here and here. It goes through the y and the z-axis here. Okay. So if you take a look at this, we still have an origin right there. That's the point now 0, 0, 0 instead of just 0, 0. And we separate this into 8 octants. So what's positive, what's negative? Half of them are positive for x, half of them are negative for x, and so forth and so on. The first octant is the one where everything is positive, and so we spend a fair amount of time thinking about that. We also order things with an ordered triple instead of an ordered pair, x, y, z. And x is the directed distance from the yz plane to p. In other words, how far did I go in the x-axis? Right. You got a bunch of points shown here, and I'm going to pause the video here and see if I can zoom that in a little bit for you. I'm not sure that's a ton easier for you to see, but hopefully you can kind of see what's going on here. We've got various points put out here. And you can see right here is the point 3, 3, negative 2. And so I've come out 3 units on the x-axis, over 3 units on the y-axis, and then from here down 2 units. And you can see various other points done similar. We're going to give a try to one of these, and then I'll let you do the next one on your own. Here's the point 3, 4, 1. So let's just go ahead and start with that. What I want you to think about here is you're doing a lot of parallelograms here to just draw one point. And so to start out, we take the point, the x-axis, we go out 3 units. So 1, 2, 3. Remember, this is the x-axis. Get my pen handy. Right there. All right. And then it says we go 4 units on the y-axis. Now, I like to go just 4 units on the y-axis first. See if I can draw that in fairly well. Alright, and now what I'm going to do is hopefully draw in that parallelogram. So I stay parallel to the y-axis. I go here, and this is supposed to be parallel to the x-axis. It's hard for me to do this with my mouse. Alright, and the final one, it says go up 1 unit. So I go up a unit here in the z direction. I go up a unit from that point, and from this point. And my goal then is to draw this box, if you would. You might say, Mr. Ring, that is a lot of work to draw one point, and you are correct. But and if we were able to, I'd make all of these dashed lines, and so all you would see really is that point right there. So the point we're really trying to focus on is right here. That is the ordered triple, or the point 3, 4, 1. I want you to try that with the other one and see how you do. It's 2, negative 5, 6, so you're going to come out 2, and the tricky part, you're going to go back to the left 5 units and then still up 6. So go ahead and try that. Use this as a reference. All right. How do I find the distance between any 2 points? Well, you know the distance formula in 2 space. It is really not different in 3 space, except for we add 1 dimension. So the distance is equal to x sub 2 minus x sub 1 quantity squared. So in this problem, that is 2 minus 3. squared plus, and then negative 5 minus 4. And remember, you can put them in either order because you're squaring each difference. Plus, and then finally the last one is 6 minus 1, which I think I could do that one in my head, but we'll still write it out. So the distance between these 2 points, 2 minus 3 is negative 1, squared is 1. Negative 5 minus 4 is negative 9, squared is 81. Remember, these all have to be positive. Try it in your calculator and you get a negative number, you've done something wrong. 6 minus 1 is 5, squared is 25. That to me looks like 26. 82 plus that is the square root of 107. So that's the distance between those 2 points. Did I have to graph them? No, although you just did. But you can get a sense of the distance without knowing anything about it. How do I know midpoints? Well, the midpoint formula, remember, is it's halfway between one point and the other. So if I said what is the m midpoint here, it's going to be a point as compared to a distance here. It's simply halfway between them. So what's halfway between 3 and 2? I take 3 plus 2 and divide by 2, comma, I take halfway between 4 and negative 5, so the average of them basically is 4 plus negative 5 divided by 2. And finally, halfway between 1 and 6, 1 plus 6 divided by 2. Notice we're subtracting with distance, adding with midpoint. People get those mixed up a little bit. And so this is simply the point 5/2. This is going to be negative 1/2. And I think that says 1 plus 6, so that is 7/2. Right? There's your midpoint. All right, if xyz is some arbitrary point on the sphere, okay, it's a point on the sphere, you can see it right here. The equation of the sphere is given by x minus x naught squared, quantity squared, plus y minus y naught, quantity squared, plus z minus z naught, quantity squared, equals r squared. Boy, that sure looks like a lot like the equation of a circle, but remember the definition of a sphere is the set of all points in space equidistant from a given point follow the center. Definition of a circle, set of all points on a plane equidistant from a given point called the center. Okay, so how would I find the equation of a sphere with center 3, negative 8, 4, and radius 7? Well, this replaces your x naught, this replaces your y naught, this replaces your z naught. And so we just substitute, put those values in, really straightforward. X minus 3, quantity squared, plus y plus 8, quantity squared, plus z minus 4, quantity squared, equals, and again this is r squared, r is 7, so it's 49. There you go, not too tough. Alright, and it says, moreover, the midpoint of the line segment joining these 2 points has coordinates, and we already did midpoint, so. Alright, in space, vectors are denoted by ordered triples. So the 0 vector is 0, 0, 0. Unit vectors, I, which is now 1, 0, 0 instead of just 1, 0. J, which is 0, 1, 0. And K, which is 0, 0, 1. K is the newcomer to this, in the direction of the positive z-axis. The standard unit vector notation is V equals V1 times I plus V2 times J plus V3 times K. So that is that linear combination we talked, or that combination we talked about before. Okay, and you can see what's happening here. Here's an I, here's a J, here's a K, and then I've got some vector out here. Okay, what is the standard unit notation for vector V at 2, 9, negative 4? And we can draw that out if you'd like. I'm going to not do that here to save time. So I'm going to say that vector v is equal to, just take the 2, it's 2i, plus 9j minus 4k. And that's it. You might say, man, this chapter's pretty easy so far, or section, and you're probably right. Alright, if v is represented by the directed line segment, so basically we did this in 2 space, now we're doing it in 3 space. We'll just take the terminal point minus the initial point, and we're going to do the same thing here. Notice it's a directed line segment from P to Q, which means this is my endpoint, terminal point, this is my initial point. So V is equal to, and to save time, I'm not going to write it all out, it's 1 minus 7, so that's negative 6, comma, 5 minus negative 3, which is 8, comma, 9 minus 6 is 3. And I just put that in there. So we're good to go there. We have vectors in space. And this talks about just, I want you to read through these, the magnitude. All of these are basically the same thing. We've just added a 3rd dimension to it. And everything else looks exactly the same. Look it over. It says, let's find the component form and magnitude of vector v having initial point -2, 3, 1, and terminal point 0, -4, 4. So first, of course, we need to find vector v. And this is the terminal point, so 0 minus -2 is 2. -4 minus 3 is -7. 4 minus 1 is 3. Okay, so that's its vector. The magnitude of v, ooh, nice writing, is equal to the square root of 4, which is 2 squared, which is 4, plus 49, plus 9. And I'm kind of hurrying through this. That's equal to the square root of 13 plus 49 is 62. Right? So here's my vector v. Here's the magnitude of that vector. To find the unit vector in that direction, u is equal to, notice this is u, not v again. It's just this component, 2 divided by the square root of 62. Now, if you want to rationalize these, you certainly can. But for right now, we're just going to get this part done. There you go. And there you have your unit vector. Its length, again, is 1 in the same direction as that vector there. All right. We're going to talk about parallel vectors here as well. And you can read through this if you would, please. Parallel vectors happen when one is a scalar multiple of the other. That's all it is. So you see 1 is a scalar multiple of the other. U is equal to some scalar times v. Let's take a peek at this. Vector w has initial point 2, -1, 3, and terminal point -4, 5, 7, 5, which, if any, of these two vectors is parallel to it. So first, we need to know what is vector w, of course. You can't just use the points. We need to find the vector form. So that is equal to -4 minus 2 is -6. 7 minus -1 is 8. 5 minus 3 is 2. And so I have vector w. Now, is either one of these, if I multiplied w by some number, would I come up with u or v or vice versa? So w is equal to, if I look at this carefully, vector w is equal to, well, take the first one by, looks like -2, I'll get that. I take that by -2, I get that. Yeah, it's -2 times vector u. Hence, u and w are parallel to each other. They're parallel vectors. Now v, let's see, w is equal to, well, to make that work, it would have to be -1/2, right? -1/2 times 12 is, I'm about out of time. I got to stop. So you can look at that one and find out the answer. Thanks for watching.